Hi everyone, I'm Sandy Lucas. I'm the Program Manager for the Climate Variability and Predictability Program at NOAA. Thank you for joining us for this webinar series called Years of Maritime Continent Piston Field Campaign. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. If you've missed any of the prior talks in past CVP webinars, I encourage you to view them from our website. All sessions from this program that have been recorded so far have now been posted, so please check them out. The Years of Maritime Continent is an ongoing set of international field campaigns and modeling efforts focused on the Maritime Continent region. YMC is led by the countries of Japan, Indonesia, and the US, in partnership with several others. Of particular interest to NOAA and the Climate Variability and Predictability Program is to improve understanding of processes that affect the propagation of interseasonal oscillations, such as MJO, in the Maritime Continent and its broader regions. MJO is important to local weather and climate, as well as having global teleconnections. However, the Maritime Continent region can sometimes act as a barrier to the propagation of MJO, and weather and climate models have a hard time reproducing this effect. In response to that need, the CVP program solicited for observation and modeling projects that investigate different processes that affect the MJO. Additionally, in collaboration with the Office of Naval Research, CVP supported several activities of the Piston Field Campaign. This year's webinar series covers the 16 projects funded by CVP. I look forward to hearing their results in this webinar series. I would like to thank Gabriela Giliazkov, the CVP student visitor and the organizer of this series, for all the hard work that she has done since July putting this series together. She has done a great job working with each of the presenters, and the success of this effort shows her hard work and dedication. At this point, I'll turn it over to Gabriela for the full introduction of this series and the introduction of our speakers today. Gabriela, whenever you're ready.
Thank you, Sandy. Hello, everybody, and welcome to the 5th of 10 webinar sessions on the topic of Years of Maritime Continent, which will feature 2 presentations per session and will run from September 10th, 2020 to March 11th, 2021. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned with a broader scientific community. We hope you will enjoy today's talks and ask plenty of questions. As you listen to the presentations, if you have a question you would like to ask the presenter, please raise your hand. Raise your hand is a feature which you can find on the control panel for GoToWebinar. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using their audio. If you have audio problems, I will ask you to type your questions into the questions box, which can also be found on your control panel. Our first speaker today is Toshi Shinoda from Texas A&M University. Toshi currently works at Texas A&M University, Corpus Christi. His major research areas include air-sea interaction in the tropics and subtropics. His recent work mostly focuses on upper ocean mixing processes and air-sea interactions associated with the MJO and atmospheric rivers. Toshi, thank you so much for joining us, and at this time, we will turn the controls over to you.
First, thank you for giving us the opportunity to present our work here. So this is a project title, and we've been focusing on the upper ocean processes in the maritime continent. And then these are the team members. This is a collaborative effort between Texas A&M University, Corpus Christi, Woods Hole, and NOAA. So today, we're going to introduce 2 most recent work related to upper ocean processes. The first one is the extreme cooling event associated with the Banda Sea, the MJO in the Banda Sea in 2015. And this part of work has been done mostly by one of the team members, Suyan Pei. And John Stephan is gonna talk about regional coupled modeling on tidal mixing effect over the maritime continent. Okay, so the first topic here is an extreme cooling event in a band of sea, here band of sea, associated with the MJO that happens in 2015 boreal winter. So this is an overview of the band of sea ocean response to the MJO forcing. So this is the MJO composite of OLR anomaly. You can see the convection associated with the MJO is located over the maritime continent in phase 4 to 6. And this is the band of sea, and this is phase 5. So you can see the strong convection here. And this is the surface forcing fields in the band of sea. So this is the area average of this rectangular region. So this is precipitation and zonal winds and the meridional winds. So at phase 4, you can see the maximum precipitation occurs, and a little later you see the strong zonal winds in the band of sea. And in response to these surface forcing fields, SST cooling occurs, and around phase 4 to phase 7, cooling continues, and amplitude is something like 0.3 to 0.4 for the composite. And this is consistent with the previous work, Napitu et al. 2015. And they also suggested that this SST intra-seasonal variation is primarily driven by surface heat fluxes. Okay, so this is the 2015 event. So this is a time series of sea surface temperature for each MJO event in each year. Here, we selected the event which produced the largest SST cooling for each year. And this time 0 is the minimum sea surface temperature. And you can see 2015 is quite different. First, the amplitude is very large, 2 degrees C in a basin average. And the second cooling rate is much larger. Its rapid cooling happens in about 11 days and 2 degrees C. So there are some other event comparable amplitude, and 2007 is even bigger. And this is another extreme event. So we're going to compare this 2015 with the 2007 later. And if you look at the MJO amplitude, so this 2015 is relatively strong, but not extreme. But in terms of ocean temperature or sea surface temperature, it is extreme. And we look at other SST product, and which is quite similar. And you can see the extreme here in 2015 and 2007. Okay, this is the 2015 MJO, and left panels are the OLR anomaly, and event happens in December. So this is mid-December, and in late December you can see the strong convection over the maritime continent. And this is the surface winds and wind speed. So in early and mid-December, you can see the weak winds, and originally it is easterly, and then becomes westerly, and in late December, you see the very strong westerly winds here in the entire band of sea. And this is SST, and you can see the early to mid-December, SST is very warm, and rapid cooling occurs in late December, and you see a lot of cold water in the entire basin. So this is the OLR anomaly longitude time plot, and this is east and this is west. And you can see the eastward propagation in the mid-December. The convection is located around Banda Sea area. And so you can see the after the strong convection, you see the very strong winds in mid-December to late December. Okay, so this is the sea surface temperature for the basin average from several different SSD products. And you can see the similar large cooling, very rapid cooling here in association with a strong winds. And this is much smaller than climatological sea surface temperature. Okay, so to examine the ocean processes or physical processes, we conducted one-dimensional ocean model simulation. Here we use a PWP model. And the model was forced with basin average surface forcing fields. And this is surface heat flux. This red one is the shortwave radiation. And the blue one is a latent heat flux. And consistent with other studies, you can see this reduction of shortwave radiation during the active phase of the MJO from mid-November to mid-December to late December. And also you can see the increase of latent heat flux, and in combination of these two, you see the net heat flux negative, so it's cooling at the surface. And also you can see the strong wind, and this strong zonal wind happens in mid-December to late December. And this is the one-dimensional model results. And this is a depth and a time plot. And you can see, so this solid line is the mixed layer depth, and you can see the very rapid deepening of the mixed layer, and that produces the SST cooling. And this is the lower panel is from the high resolution ocean reanalysis. And this is here, this is from the HICOM reanalysis. And you can see the similar pattern of mixed layer and sea surface temperature. So one-dimensional is able to simulate this variation very well. And so this is the sea surface temperature averaged over the Banda Sea basin. And you can see the large cooling, which is about 2 degrees C, can be simulated by one-dimensional model very well. So this suggests that this extreme cooling is primarily driven by one-dimensional processes. That's the surface heat flux and vertical mixing. So we look at the each term, surface flux and vertical mixing for this simulation. And this blue one is entrainment cooling or vertical mixing. And the purple one is surface heat flux. And you can see both are significant and contribute to the cooling. But you can see the vertical mixing is larger than surface heat flux, unlike other MJO events. So, okay, so the primary process to drive SST cooling is a one-dimensional process, as suggested by model, but you can see this one-dimensional model somewhat underestimate the cooling near the end of cooling period. So this could be due to the three-dimensional ocean process. So then we look at the three-dimensional processes here. So the left column is the 20 degrees C isotherm from the high-resolution reanalysis, and you can see the so the 1, 2, 3, 4 corresponds to these dates. So 1 is the beginning of the cooling, and 2 is the middle of the cooling, and 3 is near the end of the cooling, and 4 is the end of the cooling. So if you look at the thermocline depth, you can see the very shallow thermocline along the coast, and this suggests a strong upwelling here. And if you look at the sea surface temperature, you can see the very cold water near the coast. And this arrows surface currents. In late December, you can see the northeastward currents produced by the westerly winds. And this currents brings this cold water to the middle of the Banda Sea Basin. So this suggests that this cold water advection influence the SST, and we look at the horizontal advection term. Then you can see in a large portion in the cooling that is caused by this cold water advection. However, you can see also a warm water advection here, and that can partly cancel this cooling. So what happens here is you have the currents towards the from the southern side of the islands to the Banda Sea Basin. So if you look at the sea surface height change here, this is the Banda Sea Basin, and the sea surface height decreases a lot along the coast and increases. So this decrease is associated with the upwelling, and the increase is associated with the downwelling, and that produces the large pressure gradient that drives this currents towards the Banda Sea. And if you look at the sea surface temperature, the southern side of this island is much warmer than the Banda Sea, the waters, and this brings the very warm water to the basin. So this warm water advection also contribute to the sea surface temperature. And the net is cooling here, but it is canceled out by warm water advection. So this around here, this cold water advection contribute, but for the basin wide, it is not as strong as the vertical processes, such as vertical mixing. Okay, so 2015 is the El Nino year. So we argue that this strong El Nino in 2015 is partly responsible for the extreme SST cooling. So to demonstrate that, we first compare the 2015 event with 2007 event. That's another extreme event shown in the first slide. So 2007, you can even see the larger amplitude of cooling. And the 2007 is a strong La Nina year. So we expect that different ocean processes happen during this event. So first look at two events. So this is the GPM precipitation, and this is the longitude and the time. And this is 2015 event. You can see relatively strong MJO event pass through band C in mid to late December. And if you look at 2007, zonal extent is much larger. So that means anomalous forcing lasts longer than 2015. And this is a SST from different SST products and the 1D model. You can see the rapid cooling in 2015, and the 2007 you can see the similar large amplitude, but the cooling is slower than 2015, and surface heat flux is larger than in 2007 than 2015, and the wind stress is somewhat similar, the amplitude, and the precipitation is heavier in 2007. Okay, so we argue that the very shallow thermocline associated with the 2015 El Nino in the Band C area is partly responsible for the extreme cooling. So to demonstrate that, we did additional 1D ocean model simulations. So this is the thermocline depth in 2 events. So this is December and January, and this blue line is the 26 degrees C isotherm depth during 2015 event, and the orange line is the 2007 event. So this dashed line in the climatology, and you can see the thermocline is much shallower in 2015 El Nino, and the 2007 La Nina, the thermocline in a Band C is much deeper. So here we use initial condition of these 2 situations. So the first experiments, this is just the one shown in the previous slide, 2015 surface forcing fields and 2015 initial condition. And the second event is the same forcing, but initial condition is the 2007, in which the thermocline is much deeper. Note that the sea surface temperature is quite similar in two events in this period. And other sets of experiments similar to 2015. This is a 2007, the forcing field with 2007 initial condition, and the second one is 2007 surface forcing and 2015 initial condition. So this is the results from the 2015 MJO forcing. So the blue line is the initial condition of 2015, which is the same as those shown in the previous slides. So you can see this SST cooling, it's about 2 degrees C, which is observed. And if you use the different initial condition 2007, which is much deeper thermocline, then this cooling is largely reduced, and this is only 1.5 degrees cooling. And if you look at the heat budget, the entrainment cooling or vertical mixing is largely reduced due to the deep thermocline that causes the much the smaller amplitude of the cooling. And if you look at the 2007 event, you can see the similar results. 2015 initial condition case produced is a much larger cooling, and also entrainment cooling or vertical mixing is larger in 2015 event, which is a 15 initial condition case, which is a much shallower thermocline. So these experiments demonstrate that this elevated thermocline associated with the 2015 El Nino is partly responsible for the extreme SST cooling in 2015 event. Okay, so this is the conclusions. So we found the substantial basin-wide SST cooling in the Banda Sea, which occurred in only 11-day period during 2015 MJO event. And such rapid and large cooling associated with the MJO has not been reported, at least in the last few decades. So we did a one-dimensional ocean model simulations to understand the processes. And that show that the vertical mixing contributes more than surface heat fluxes for driving the basin-wide SST cooling during this event. And the primary process is the one-dimensional process, but the three-dimensional processes such as coastal upwelling around islands in the southern basin and advection of upwelled cold waters by MJO-induced surface currents also contribute to maintaining the basin-wide cold SST. So finally, so based on the comparison with another MJO-induced extreme cooling event during 2007, strong La Nina, it is demonstrated that the elevated thermocline associated with 2015 strong El Nino largely contribute to the intensified cooling generated by the vertical mixing of colder subsurface waters. Thank you.
Thank you so much, Toshi. At this time, it looks like we already have a question from Tim Lee. Tim, I'm going to go ahead and give you permission to unmute yourself. You may need to unmute yourself on your panel as well.
Thank you, Toshi, for the interesting talk. I just wondering, there's two different questions. One is you talk about cooling. How about extreme events for the warming? What is the amplitude of the warming associated with MJO forcing? Do you have any idea? Another is what is the average amplitude of the SST response to the MJO forcing, based on your understanding?
Well, okay, so okay, so this is a composite and somewhat typical warming and cooling.
Only
So
0.2.
yeah, well, the composite, so each event, the composite tends to underestimate, but typically maybe a little more than 0.3 or something. Yeah, standard deviation is something like 0.5, 0.6. The composite somewhat underestimate. So, and well, the warming, it's a little smaller than cooling, but it is comparable.
For the extreme events, you talk about 2-degree cooling. So
we haven't looked at the extreme warming event. So yeah, I don't. Yeah, I haven't looked at it yet.
Okay, thank you.
It looks like we have another question from Shirong Zhang in the questions box that says there are large meridional gradients in SST and SSHA from HYCOM. Are they also in the observation?
Okay, so sea surface temperature, sea surface height is seen in the observation, satellite observations, and okay, so this is well, okay, so this SST gradient is difficult to resolve in SST product, and there's a high SST products high resolution SST product, but we are not sure how reliable in these areas. So yeah, we don't know the observed SST.
And it looks like we have time for one more question. I'm going to go ahead and unmute Janet Sprinthal.
Hi, great talk, Toshi. Thanks very much. Actually, I'm just interested, it's sort of an aside, is the diurnal cycle in SST that we can see on this plot, and that becomes muted, right, as the MJO event progresses. Is that just because of wind mixing?
Yes. In a suppressed phase, usually the diurnal cycle is smaller, and the SST diurnal cycle is nearly zero around this strong wind mixing period. And in this particular event, the mixed layer depth diurnal cycle is really small and negligible around here. So yeah, so this SST, no diurnal cycle in SST is consistent with the previous studies.
Thank you.
It looks like that's all the time that we have for questions. At this time, we're going to switch over to the next presentation. Thank you so much, Toshi. Up next is a presentation by John Steffen from the Woods Hole Oceanographic Institution. John received his PhD in meteorology from Florida State University in 2018, where he worked with Mark Bourassa on observing and modeling oceanic barrier layers interacting with tropical cyclones. He is currently a postdoctoral investigator at Woods Hole Oceanographic Institution, working with Yude So on high-resolution coupled modeling of the MJO. John, thank you so much for joining us, and at this time, we're going to go ahead and give you presenting ability.
Great, thank you, Gabriella, for that introduction, and to Sandy and Victoria also for hosting this webinar series and inviting us to present some of our work. Okay, so today I'll be talking about the role that tidal mixing plays in modulating the MJO SST coupling in the maritime continent. And I'd like to introduce our collaborators on this work, Hyode So and Caroline Clayson at Hui, and also Suyang Pei and Toshiaki Shinoda at Texas A&M Corpus Christi. And so I'll begin today's talk with a brief review of the importance of the ocean in the climate system in the maritime continent. And so this figure on the right here is showing the Indonesian through flow pathways from Sprintonal 2014. And so the maritime continent is composed of over 17,000 islands, and it's situated in the tropical Indo-Pacific basin, separating the Western Pacific and Eastern Indian Ocean. And the ITF transports warm and salty Pacific waters through the Makassar Strait and other ocean pathways into the Indian Ocean. In this region, support some of the warmest sea surface temperatures in the tropics, and tidal mixing within these seas produces a water mass transformation and a reduction in the time mean SSTs here. And so if we look at some of the tidal mixing signatures in the Banda Sea and also some of the other marginal seas of the maritime continent, various observational and ocean modeling studies show that there's a reduction in the regional SSTs of approximately 0.3 degrees Celsius to 0.5 degrees Celsius. And there's some longer fortnightly and monthly periodicity at about 0.1 degrees Celsius as well. And so this figure on the right here is showing a temperature and salinity diagram of observations in black within the Banda Sea region. And this is a region where the water column is pretty nicely mixed here to tidal mixing. And we can see a comparison between our the no tides run in blue to a tides run in red. The water mass is improved compared to observations when you include tides. And so the vertical mixing that's induced by the tides moves heat and fresh water down into the thermocline, and this can affect the radiative convective equilibrium of the atmosphere. I'll also note that using a bulk formula for for surface fluxes, a decrease in the SST of about 1/4 degree Celsius produces a latent heat flux decrease of about 10 watts per meter squared. And this is a magnitude that's comparable to the observed MJO-induced SST and heat flux variability of about 0.4 degrees Celsius and 20 watts per meter squared. So this kind of highlights our motivation for the talk here. The tidal mixing effect on the time mean SST appears to produce cooling that's similar magnitude to the intraseasonal SST variability brought about by the Madden-Julian oscillation, and that this is potentially a mechanism for oceanic modulation of the MJO in this area. And so our hypothesis is that by explicitly resolving the tides and their interactions within with the Madden-Julian oscillation in a high-resolution coupled model framework, that we can improve the simulation of MJO convection. And I'll also note that this is one of the first studies that's looking at high-resolution coupled modeling of the tides effect and how the atmosphere responds. So the scientific questions we'd like to address here are, to what extent does tidal forcing affect ocean mixing and time mean SST? How does tidal mixing influence the intraseasonal MJO SST coupling in the region? And does this have an appreciable effect on MJO convection? And to tackle these three questions, we're going to use a high-resolution score model and run a couple tides experiments. If you'd like more details on the background of the score model, you can refer to So et al. 2007 and 2014. And so the score model is a high-resolution regional coupled model that couples WRF and ROMS. On the right here, you'll see our score model domain for the Maritime continent, and I've labeled some of the important islands and marginal seas here as well. And we perform a 3-month simulation from October through December 2011, which includes 3 distinct MJO events that occurred during the Dynamo Field campaign. And for WRF and ROMS, we're using a shared high-resolution grid of 4 kilometers, and it's able to resolve convection and also, importantly, the fine-scale coastal oceanic processes that we're interested in. And I'll also note that we are performing spectral nudging of the wind field above 850 millibars at wave numbers K 1 through 3 and L 1 through 2 toward the ERA interim reanalysis. And that's just so we can get a realistic simulation of the dynamical MJO. So for our experiment design, we run a set of twin coupled score model runs with and without tidal forcing. And in each configuration, we include 3 ensemble members. To prescribe the tides, we're using the Oregon State University tidal prediction software that interpolates 13 major tidal constituents to our ROMS grid. And importantly, we're including the semi-diurnal tides and the diurnal tides here. A longer timescale tide on fortnightly and monthly timescales, and also 6-hour period tides as well. And the tidal forcing prescribes the tidal period, elevation, phase angle, and inclination angle at the ocean surface. So this loop here on the left is the ROMS hourly sea level height from our tides run over a 2-week period. And initially what stands out is you get the diurnal pulsing of the barotropic tides coming through the domain. And then also you can see within the semi-enclosed marginal seas of the Banda Sea, Sulu Sea region, this conversion of the barotropic tide to baroclinic. And you can actually see these internal waves propagating through the interiors of the ocean basins. And this is a region where there's strong tidal mixing. The conversion of the barotropic to baroclinic tides is about 20 times stronger here than in other open ocean conditions. And the near field dissipation of this tidal energy tends to concentrate over complex bathymetry such as sills and bays and channels and seamounts that really confines the strong SST cooling response But you also get a far field dissipation too from these internal tide propagations, and also advection through ITF pathways. So the first thing we want to do is just make sure that our tidal forcing is representative of real life. So we're going to do a comparison to the University of Hawaii sea level center that has tide gauge information for this region. On the right, you can see all the locations where there are tide gauges in the Maritime continent. And the red circles here highlight the 8 locations where we have hourly sea level observations during our period of study. And we'll compare these sea level height measurements to our ROMS model to make sure we're providing a reasonable estimate of the semi-diurnal and diurnal tides, which are primarily responsible for tidal mixing here. And so on the left-hand side plot, I'm just showing a power spectrum here of the sea level height from our ROMS tides run in blue compared to the sea level height moorings in magenta, and also compared to a red noise spectrum. And immediately what you see that stands out is you have these 2 strong peaks at our semi-diurnal and diurnal tidal periods or frequencies that have a statistically significant peak here. We can also look at that in the middle figure in period space. So we can once again see we're looking at semi-diurnal and diurnal tides. And then if we do a magnitude squared coherence comparing our ROMS tides to the observations, we see that there are strong peaks at about 0.8, indicating strong correspondence between our model runs and observations. And so overall, the ROMS tidal forcing that we're prescribing is able to accurately resolve the tidal elevations in the Eastern Maritime continent compared to these observations. So we can also take a look at the ROMS tidal currents. The right-hand side figure here is showing the magnitude of the tidal current speed and their locations within the Eastern Maritime continent region. I've also plotted vectors for any locations where the tidal currents are above 0.4 meters per second. And we can zoom in here in an area within the Banda Arc region and take a look at what the time series of the surface current speed looks like. And so plotted in red in this time series, this is about a 21-day time series of the tidal currents at this point. In red is the no tides run. So we can see there's some synoptic variability that's evident here. But more importantly, in the tides run, we have this high frequency tidal current superimposed on this kind of longer synoptic variability. And so the stronger tidal currents here support enhanced shear-driven mixing. And I'll also note that the locations of these strong tidal currents are highly correlated with the spatial pattern of SST cooling here. So to get into some of the oceanic results and SST response to tidal forcing, we can take a quick look at the basin average sea surface temperature response here. So on the top figure is a time series of the basin average SST. In black and gray, we have 2 satellite-derived SST products. Black is the Noah Reynolds SST, and gray is the Seaflux CDR SST, which includes diurnal heating. So kind of the shape of the observations is similar, but the Seaflux data is offset by about 0.2 degrees Celsius above the Noah Reynolds SST, just to being able to resolve this diurnal heating. Our modeled SST is shown in red for the no tides run and blue for the tides run. And so immediately what we can see is that the modeled SST, we're able to reduce the high bias in the SST in the model by including tides. The bottom figures here are just showing the spatial structure of the SST field, where Noah Reynolds is on the left-hand side plot and our model runs are on the right-hand side plot. And once again, when we include tidal forcing here, we're able to improve not only the high bias, but also the spatial SST pattern, especially near the Sulu Sea, the island of Sulawesi, the Banda Arc region, and the Lesser Sunda Islands down at the bottom of the domain. So what does the SST difference field look like between our tides and no tides run? And that's what I'm showing here on the left-hand side. So our spatially average SST cooling over this whole domain is about 0.27 degrees Celsius, which is a similar magnitude to the intraseasonal SST variability from MJO passage. And we have some very strong cooling, upwards of a degree Celsius, that occurs near the Sulu Sill and Lesser Sunda Islands, for example. We can further look at the time series of the SST difference subset based upon these regional locations. And one thing immediately sticks out here is that the magnitude of the SST cooling is dependent upon MJO phase. And so if we highlight the MJO2 that starts towards the end of November and continues through the early first week of December, the cooling is enhanced here. And that's due to more wind forcing associated with the active MJO2 phase that intensifies the SST cooling. But one really important part to tidal cooling is that most of the bulk of the cooling actually occurs in the subsurface. So the largest temperature differences when we prescribe tides actually occurs near the base of the mixed layer. And so if we look at a depth time cross section here of the SST difference field, we see that the largest cooling of about 2 degrees Celsius actually occurs at a depth near 40 meters. I've also overlaid the isotherms here from our tides run. And the way that the subsurface cooling is connected to SSTs here is through enhanced wind mixing associated with the active phase of the MJO. So I've also shown a time series here of the total wind and U wind for this period below, and then also a zoomed in contour of the from the surface to 10 meters above that really highlights that starting December 1st, when the active MJO starts, the surface from the surface down to 10 meters cools pretty dramatically. And so this is consistent with previous studies that have linked monsoon phase-dependent tidal mixing and its effect on SST. The only difference really here is that we're looking at intraseasonal SST instead of a seasonal monsoon-driven SST cooling. Another interesting fact from this modeling study is how the near-surface stratification changes in response to subsurface cooling. And so I've also plotted a depth time series here of the n-squared difference between the two runs, and contour lines here are showing the SST or the temperature reduction. And so above the maximum cooling here, we actually get an increase in the stratification because the thermal stratification is actually being increased. And when the active MJO enters the domain here on December 1st, this enhanced stratification is being eroded by wind-driven mixing. And this is kind of similar to the mechanism of the diurnal warming, where during the suppressed phase of MJO2, you actually get an increase in near-surface stratification, and that gets eroded during the stronger wind forcing as MJO propagates through the region. So I'll also connect this to some of our atmospheric results and how the SST cooling here affects our surface meteorology fields, also diurnal convection and deep tropospheric drying. So if we take a look at our surface meteorology fields, they generally respond according to what we'd expect to a reduction in SST, namely that the 2-meter air temperature and humidity are reduced. So that's in green and kind of our brown colors in the middle. And that there's less latent heat flux on the left-hand side plot and an increase in outgoing long wave radiation that's indicative of less precipitation during this time period. Dwarf precipitation is reduced by about 5% when we prescribe tidal forcing to ROMs. And this results in a slight improvement in the high bias in precipitation, especially at diurnal timescales. So if we take a look at the diurnal cycle of convection in the maritime continent, on the y-axis here, we have the average precipitation rate composited over local time on the x-axis. Now I've broken this up into our no tide and tides runs, so no tides in red, tides in blue. And I've also broken it up by land-based precipitation versus sea-based precipitation. And as you can see, we have a reduction in both of those due to the SST just being cooler in this region. And we can compare it to a similar plot for TRIM and CMORPH estimates of the average precipitation rate. And we can see that there's a well-known high bias in precipitation coming from WRF when we compare it to observations. And this is especially true over land. And we slightly improved that by introducing tides. And I'll also note that the phasing of the diurnal cycle is fairly consistent between observations and the WRF model. It's not too far off, with land-based precipitation peaking in the early afternoon and sea-based precipitation peaking in the early morning hours. I'd also like to introduce this idea of the moisture mode paradigm in modulating the Madden-Julian oscillation. And so this figure from Chen and Wang 2020 is showing the dynamic mode of MJO being connected to moisture mode, how the atmospheric moisture changes with time can affect convective heating and also MJO dynamics. And that moisture mode of MJO is dependent upon the base state moist static energy, which is a function going to be highly related to the underlying SST. And so previous studies show that the low and mid-level moisture convergence are responsible for MJO propagation. And we think that tidal forcing, which rectifies SST in this region, may have an impact on this moisture mode feedback to MJO in the maritime continent. And so we can look at how the moisture field is responding to changes in SST. If we look at a pressure time diagram of our difference in the mixing ratio between our tides and no tides run, we see that there's deep tropospheric drying throughout the entire simulation, and that drying is enhanced during the active phase of MJO2 here, the early part of December. I'm going to play another set of movies here of column integrated moisture, where the left is from our tides run and the right movie is from the difference field. And we can see that there's quite a bit of spatial and temporal variability in tropospheric moisture, yet there's enhanced drying when we prescribe tides, especially over the eastern MC domain. So to conclude, I'd like to circle back to our first three scientific questions and provide a summary of what I've shown here today. To what extent does tidal forcing affect ocean mixing and time mean SST in this region? And we've shown through high resolution coupled score model runs that the eastern maritime continent basin average has an SST cooling of about 1/4 degree and regional cooling on a smaller scale of about 1 degree Celsius, which generally alleviates the high SST bias in the model. And how does the tidal mixing influence interseasonal MJO SST coupling? The largest tidally induced cooling occurs at the base of the mix layer, and this is manifested at the surface through strong wind-driven mixing during the active phases of MJO. So the SST cooling due to the tides is MJO phase dependent. And furthermore, does tidally induced cooling affect MJO convection? And we've shown that in WRF, the high bias in WRF precipitation is reduced by about 5%, which is moving in the right direction. And so with that, we've shown that tidal forcing is of oceanic origin, and it produces a sizable SST anomaly in the maritime continent that's dependent upon MJO phase. And so I'll leave everyone with a couple of questions for further work or further discussion. Is this SST anomaly a significant source or sink of MJO predictability? And further, is the basin scale cooling large enough to contribute to the MJO barrier effect? And so with that, I'll take questions. Thank you.
Thank you so much, John. Looks like we already have a question from Clevin Richards. Clevin, I'm going to go ahead and unmute you.
I was impressed by the impact that tidal mixing has on both the ocean and atmosphere. I have two questions. One is, how do your estimates of tidal mixing compare with other estimates? And the second question is, you noted the propagation of baroclinic tide away from generation regions. Are you able to quantify in any way the impact of locally dissipated tides compared with tides being dissipated in the interior of ocean basins?
Okay, to address the first question, I think the magnitude of our SST cooling due to prescribing tides here is in the ballpark of other estimates. I showed that it's about 0.3 to 0.5 in a regional SST difference. We do have regions that are quite a bit stronger than that. Near the Lesser Sunda Islands and the Sulu Sill, we're near 1 degree Celsius. But on a basin scale average, we're at about 1/4 degree, which is, I think, consistent with previous literature. In terms of kind of the relative effect between near field dissipation versus far field dissipation, most of the SST cooling response is occurring near the tidal mixing kind of generation sites where there is that conversion. And yeah, certainly there is some propagation of that into the far field, whether that's produced by internal wave propagation or also, I think, advection just by the ITF pathways will also contribute quite a bit to that. We haven't quantified the relative sense, but in the previous literature, I think most studies attribute that to the near field dissipation over those local hotspots.
Okay, thank you.
We have one more question from Janet Sprinthal. I'm going to go ahead and give you permission to unmute yourself.
Oh, terrific. Thank you very much, John. That was a really inspiring talk. There's been a couple of schools of thought that the fortnightly tidal cycle has a big impact on SST, depending on which phase you're in. Field and Gordon, for example, and many others over the last decades, and it's unclear. Have you looked at whether the phase of the fortnightly cycle matters for the MJO reaction or anything like that? It's a really badly formulated question, but I think you understand what I'm trying to get at.
Yeah, I think I understand. Yeah, it's something that we've thought quite a bit about as well. And it's an interesting question. Yeah, I think Field and Gordon showed that at fortnightly and monthly periods, the SST can fluctuate by about a 1/10 of a degree. Mm-hmm. In our modeling study here, we have a little bit trouble diagnosing that because we're only performing model runs that are 3 months long. So we're a little bit constrained by the length of our model runs here. Maybe performing some longer model integrations, we could look to see at that kind of longer periodicity of the SST signal. But at 0.1 degrees Celsius, I think that definitely could be influential. That's a significant portion, a fairly significant portion of our basin average SST difference, which is about 1/4 degree.
Right. Yes, and I understand that impact is even stronger. The fortnightly signal is even stronger, like away from the coasts, where away from the generation sites, the sills and places like that. So it's just considering. Thanks very much.
Yeah, thank you.
Thank you again, John. We'd like to thank you for joining us for this set of presentations in our series on Years of Maritime Continent. I would like to thank today's presenters for taking the time to share their work with us. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/CVP. We will be taking a break from our normal biweekly webinar schedule for the holiday season. Our next webinar will be on January 14th, 2021. We hope to see you then. Thank you.